Okay, hello. So in this video, I'm doing section B.5.4, and this is part of section B.5, which is the epsilon-delta definition. So B.5 is the epsilon-delta definition. B.5.4 is right at the end of that chapter, or that section, and it is all about other types of limits. What do I mean by other types of limits? Let's remember what we did in week 1 of this course when we did limits. So I'm going to show you the Epsilon Delta Explorer. This is the green zone. And here I have the function. The function f of x is 1 over x squared. F of x is 1 over x squared. And this was the function we looked at in week 1, where we said, by the way, here I'm looking at around the limit as x goes to 0. And I'm trying to see is the limit 5. And the problem is the limit is not going to be 5 because the function, no matter how small I make this blue zone, no matter how small I shrink the delta value, the function is always exploding out the top of the green zone. So no matter how small you shrink around x equals 0, there's always a little piece of the function that lives way up here, way outside the green zone. And so no matter how big you try to make the limit, maybe you think the limit is 15. Well, the problem is the function eventually escapes out the top, will be above 15. And there is no value you can make the limit. There is no value where you can make this limit work. The limit will not be equal to any fixed value. And when this happens in this particular way, that it's always escaping at the top, we gave that a name, which I'm sure you know. The name is the limit as x goes to 0 of f of x is infinity. So when a limit is infinity, we are saying it's not equal to any value. It's not equal to any L value. There is no L value that works. But what is going on is the function is getting arbitrarily large. The function is exploding. It's getting arbitrarily large. And we talked about that. We talked about limit laws for that later. So we have the whole, we know what this thing means conceptually, and we can do some calculations with it. But we have not yet seen the epsilon delta definition. And that's what we're going to do in section B.5.4. We're going to do the epsilon delta definition for this bad boy. The limit, what happens when it's equal infinity. And if you remember on the Desmos Explorer, there was a little thing down here, which is the type of limit that you want to do, the value of the limit type. And type 0 was the ordinary limit, when the limit is equal to L. And type 1 and 2 were equal to plus infinity and minus infinity. So let's set this to type 1, and now the thing will change. Now, instead of trying to make a green zone that is shrinking around a point, now the green zone is sort of all the points above a certain value. So the limit now, the green zone, we're trying to trap the function in the green zone. Now the green zone is everything above a certain value. So that's the only thing that's changed. The slider with on the blue on the x-axis, that's exactly the same as before. But now the slider here is going up and down, and we're looking at values above any fixed amount. So this is what we did in week 1 when we talked about limits at infinity conceptually and with pictures. And now we're just doing it with algebra. So this is what we want. We want things to be arbitrarily large. So let's go write down what that means. So we're going to construct special definitions that work for this thing being equal to infinity. And we're going to be careful with infinity. If the height of a graph approaches a limit of infinity, so when the limit equals infinity, in quotes, instead of a number L, we can't talk about a vertical neighborhood defined by an epsilon. So in our ordinary limits, for the limit, maybe let's make a little before and after chart. So before, for the limit as x goes to a of f of x to be equal to L, that was what we had before. This was the ordinary limit. We were talking about getting arbitrarily close, arbitrarily close, and arbitrarily close meant within epsilon. So for all epsilon greater than 0, then there was some other stuff with the delta, but the part I want you to focus on, for all epsilon greater than 0, f of x minus L in absolute value less than epsilon. And this was the part that said you are close, you're within this epsilon neighborhood of L. You're within epsilon of L. That's what this stuff means. The green zone was a region of all the things within epsilon of L. That was the green zone. So you had L plus epsilon to L minus epsilon. Okay, that was before. Today is today. Today, this video, today, we're doing the limit as x goes to a of f of x equals infinity. What does it mean to equal a limit equals infinity? And we're not getting arbitrarily close. We're getting arbitrarily large. Arbitrarily large. Okay, so we don't want to be arbitrarily close. We don't want to be within epsilon for all epsilon. We want to be bigger than whatever number you think of. So no matter what number you think of, we're bigger than that. No matter what number you think of, f of x bigger than that. So that's it in words. In symbols, what is going to be? No matter what, before we said for all epsilon, now we just need a for all some threshold. Let's give this no matter what thing a name. Let's call it m. So for all m greater than 0, no matter what m value you give me, f of x has to be bigger than m. So that's exactly what the limit being equal to infinity is going to do. We're going to take the epsilon delta definition and we are going to replace the epsilon part with this m thing, and we're going to replace the green zone of, instead of it being all the stuff that is within epsilon of L, it's going to be everything that is bigger than m. So we're going to have the green zone is going to be, here's m, and the green zone is going to be everything above m. And that matches exactly what we did in week 1 in the epsilon delta limit explorer. Everything above this value. So no matter how big you make the slider, the function is above that. Okay, so let's fill in the definition here. There's a little box for us. Definition of the limit as x goes to a of f of x equals infinity. It means for all m bigger than 0, m is how big we're going to be, there exists a delta, so we can get eventually close enough. That delta part is exactly the same as the epsilon delta, so that f of x will be bigger than m. Okay, and the example is the function 1 over x squared as x goes to 0. This is exactly what we saw in Desmos. It looks like this. Crazy function looks like that. And the point is, no matter how big someone gives you an m value, it's possible to squeeze the function by looking only really, really close to x equals 0. You only look really close to x equals 0. And when you look really close to x equals 0, the entire function lives in the green zone above m. That's what it means for the limit to be equal to infinity. Okay, so I think we have the idea. We have the symbols. We have the logic. We have our muscles from doing epsilon delta proofs before. And so now we're just going to do the proof. Prove that the limit as x goes to 0 of 1 over x squared equals infinity. Okay, so first thing you got to do, what is it? What does this mean? What does it mean? It means for all m bigger than 0, there exists delta bigger than 0, so that, right? I'm just copying out the definition for this particular function. So that 0 less than absolute value of x minus 0 less than delta implies 1 over x squared bigger than m. Okay, you'll notice there's no absolute value on the conclusion anymore. In epsilon delta land, we had absolute value of f of x minus L less than epsilon. The distance between f and L was less than epsilon. But now there's no distance. We're just talking about straight big numbers. 1 over x squared, that better be damn big. Bigger than m. That's what we want. Okay. The proof is going to be, just like we did our epsilon delta proofs, we're going to start at the end. 1 over x squared bigger than m. And I better get to 0 less than absolute value of x less than delta. That's what I want to get to. Okay. So let's start 1 over x squared bigger than m. So here's a nice thing. M is bigger than 0, positive number. 1 over x squared is bigger than 0. These are both positive, and that means I can do the reciprocal of both sides. Reciprocal of both sides. And that's okay since both sides positive. So 1 over x squared positive and m positive. Okay, so when you do that, you get x squared and you get a 1 over m. And this comes with a less than. When you do the reciprocal, you flip the inequality. And that's because the reciprocal function 1 over x is monotone decreasing. Okay, so I'm at x squared less than 1 over m. I want to get to absolute value of x less than delta. Here's the thing. Here's a good fact. This is where this comes up. The square root of x squared, is exactly the absolute value of x. So square roots always output positive things. So when you do the square root of x squared, you don't get x, you get absolute value of x. In this case, this is great for us. This is what we want. So I have an x squared. I want to get to an absolute value. I'm just going to take the square root of both sides. So to do the square root of both sides, got to make sure both sides are positive numbers or it won't make sense. But in this case, they're both positive numbers. I can do the square root of both sides. Square root of both sides to get. So, okay. Absolute value of x, that's the square root of x squared. And the square root of 1 over m is the 1 over the square root of m. So there you go. I did it in 2 steps to show this thing, that the square root of x squared is equal to the absolute value of x. That's this line. Okay. All right. Hey guys, look, I'm really close. Absolute value of x less than 1 over square root of m. I want it to be 0 less than x less than delta. Why don't I just set delta to be this thing? So set delta equals 1 over square root of m. And now I have my traditional step where I drop the 0, and now I'm golden. So there you go. That is the proof. We showed that no matter what m you give me, I can find a delta that works. The delta I find is 1 over the square root of m. That works. Okay. And you have to be careful with the algebra because you have to do this trick of the absolute value. But other than that, I think it's very straightforward. These proofs are usually a little easier than epsilon delta proofs. Okay, that's it for the limit being equal to infinity. There is another definition, which means the limit is minus infinity. We're going to do this one later on. Should I say it now? I think you can probably guess what it's going to be. Let me write it down. So it's going to come up later, so you don't need to copy it into your notes. We're gonna have it later on in the notes as well. But let me just say what it is now. So here is the limit as x goes to a of f of x equals minus infinity. What does that mean? It means for all m greater than 0, there exists delta greater than 0. So 0 less than x minus a less than delta implies when the limit is infinity, we're arbitrarily large. When the limit is minus infinity, we're arbitrarily large and negative. So f of x will be less than negative m. So that's the limit being minus infinity. And that we already did the limit being plus infinity. They're sort of very symmetrical. Those are the 2 funny things that can happen with the value of the limit. In this section, there are other types of limits. That's the name of the section. There's other things that can happen. And one of them is limits going to infinity. So the limit as x goes to infinity of f of x equals L. And I'm going to do that in a separate video. So take a quick break before you watch that one and wrap your head around a limit being equal infinity. Probably go over this proof one more time. And yeah, see you in the next video.